Okay, so let's take a look at this problem. This is example 4, cooling of an automotive radiator. This is about cross flow. So a test is being conducted to determine what is the overall heat transfer coefficient for a newly designed compact water to air heat exchanger. So in this case, both of the fluids are unmixed. So we have plates that are separating the air to mix between the layers, and we have tubes that are separating the water to mix. So we have 40 tubes, 40 number of the tubes is 40, and the diameter is given 0.5 and the length is given 65 centimeter. So the rate of water is at 0.6 kilogram per second. So inlet and outlet temperature of air is given 20 and 80. So our goal is to find U. What is the U for this process? So this is cooling of an automotive radiator. So what do we know? We know T called in, T called out, T hat in, T hat out. What are we trying to find? Find U. What are our assumptions? Assume this is a steady operation. Assume fluid properties are constant. Assume changes in kinetic and potential energy is negligible. In kinetic and potential energy is negligible. Okay, so let's try to write the properties. So T mean for water is 90 plus 65 over 2, which is 77.5 degrees Celsius. At this point, Cp is equal to 4195 joule per kilogram per Celsius. T air is 20 plus 40 divided by 2. This is 30 degrees Celsius. And Cp in this condition, so we don't need this Cp here. So okay. Now we can calculate Q. So let's start to do the analysis. So Q is equal to mCp T in minus T. So for water, T out minus T in, because T out is greater. So this is for water. So the mass flow rate is given 0.6 kilogram per second. Cp is given, we just found it up, 4195 joule per kilogram per Celsius. And temperature difference is 90. We go from 90 to 45. 90 to 65, sorry. 90 minus 65. So if you carry out the math, you'll get 62.9 kilowatt. So this is Q. And what is the surface area of the heat exchanger? So we have number of tubes. We have 40 tubes. pi times di times L. So if you go back to the problem statement, we have 40 tubes. We know the diameter, we know the length, so we can calculate we can calculate the area. 40 times pi times di is 0.005 meter, and then the length is, sorry, this is, we have one extra, it's 5 centimeter diameter. Oh, sorry, 0.5 centimeter, so that's correct. Times 0.65 is the length, so we get 0.48 square meter. So now, so this is a cross flow geometry. Q is equal to F times U times A surface times delta T log mean counter. So that means if I want to calculate U, which is Q over F times A surface times delta log mean counterflow. So now counterflow, for counterflow, delta T1 is T hot in minus T cold out. Delta T2 is T hot out minus T cold in. So again, I'll just, for your information, T hot in, T cold out, T hot out, T cold in. This is delta T1, this difference is delta T2. And then we can calculate delta T1 and delta T2. So delta T1 is 90 minus 40, which is 50. Delta T2 is 65 minus 20, which is 45. So that means delta T log mean is 50 minus 45 divided by ln 50 over 45, 47.6 degrees Celsius. So now we have delta T log mean. We have Q from MCP delta T. A surface area we calculated based on the geometry. Only thing left is F. If we have F, we can calculate U. What is F? F is basically, we need to look into P and T. We have charts and tables that we need to use to find P and R values. T1 minus T2, T2 minus T1. So now let's go back to the, this is a cross flow. Both are unmixed, right? So both are unmixed. So this is the graph that I need to use. I need to read T1 and T2. So again, I go back to my definition. So I'll use this definitions here so that you remember. So go back to this definition. So T is for the tube, small t is for the tube side, big T is for the shell side. So if you plug in the numbers, water is in the tube, so T out for water is 65, T in is 90, T1 is shell inlet, so 20, T1 is water inlet, 90, so 0.36. For R, the capital T1 is shell inlet, capital T2 is the shell outlet, small T2 is water outlet, water inlet is 90, so we have 0.8. So now I need to read this graph and find the value. So P is 0.36, P is, so this is 0.35, 0.36, and R is 0.8, so 0.8 is here. So so I need to follow this line. So I have F, based on this graph, I have 0.97. So this is roughly here. So I have F value now, based on F is function of R and P and R. And this is 0.97 from the graph. So now I have everything. I can calculate U, which is Q over A surface times F times delta T log mean counterflow. And if you do the math, you'll have 3,341 watt meter squared per Celsius. So I calculated this.